Every piece of scrap casting that leaves the die eats directly into your bottom line. We're going to break down how to identify and control these defects systematically. Before we touch a single machine parameter, we must establish one non-negotiable rule. You cannot correct a defect if you cannot measure it. Without a rigid data baseline, any adjustments on the floor are just guessing. This means setting up a daily scrap reporting system categorizing by defect type, part number, specific die, shift, operator, and machine. For porosity, you also need a 1 to 5 severity rating system to track if problems are getting better or worse. Once this structured system is in place, operators have the real world data needed to track trends and mathematically prove whether a process change is actually working. This highlights our first defect, cold flow or cold lapse. The leading edge of the metal flow cools too quickly and laps together instead of fusing. To correct it, bring heat back by increasing die temperature, speeding up cycle times, or reducing die spray. Another approach is reducing the fill time. However, increasing plunger speed or size mechanically affects your entire die casting system. You must run your PQ squared calculations before making these adjustments to avoid causing new problems elsewhere. Controlling surface defects requires a careful balancing act between adding sufficient heat to the die and safely optimizing your metal flow speeds. Moving inside the casting, we run into internal defects. The first is gas porosity. This is caused by air, steam, or vaporized die lubricant getting trapped in the metal flow during die fill. This micrograph shows the precise visual signature of gas porosity. Look for unconnected spherical bubbles with smooth, shiny walls. To fix this, clear the trapped gas by checking pour rates, optimizing short sleeve delay, and ensuring vacuum channels are clean. If you identify those smooth walls, you have pinpointed an air entrapment or venting problem. You can safely ignore other machine systems and focus your efforts right there. Our second internal defect is shrinkage porosity. This has a completely different mechanical cause. As cast metal cools from a liquid to a solid, its volume naturally reduces, leaving a void at the last hot spot to freeze. Look closely at this 20 times magnification photograph. Instead of smooth bubbles, shrinkage porosity leaves a rough dendritic crystal structure inside the void. To correct this, feed more metal into the trouble spot by checking intensifier pressure and targeting cooling at surrounding hot spots. Spotting that jagged dendritic structure tells you immediately to abandon venting solutions. Your focus must shift entirely to static pressure and targeted temperature cooling. Now, let's test your eye. Here are two unmarked internal voids, based strictly on the texture of their internal walls. Which defect is which? On the left, smooth walls indicate gas porosity. On the right, rough, jagged crystals indicate shrinkage porosity. Successfully identifying this specific visual difference on the floor dictates the entire direction of your troubleshooting path. Let's consolidate this into a single tracking matrix. For surface issues like cold flow caused by cool metal edges, your primary moves are increasing die temperature and safely reducing fill time. For internal voids, texture is everything. Smooth walls mean trapped gas, so you optimize venting and short delay. Rough, dendritic walls mean material shrinkage, so you increase intensifier pressure and cool the hot spots. This matrix serves as your ultimate tool for translating visual evidence directly into targeted correct machine parameter adjustments. By applying this systematic knowledge, you take the guesswork out of your daily operations and master the die casting process right on the shop floor. Remember, true quality control begins with accurate measurement and ends with systematic execution.